Welcome to Organic Chemistry. Today we're going to look at the different ways that atoms can be arranged in a molecule, even if it's the same set of atoms that we have. So if we imagine a simple chain, you will be somewhat familiar with isomers, with normal isomers from school probably. So this would be our organic chemistry way of drawing a chemical. So let's put first of all the atoms on there. This would be CH3, this would be CH2, this would be CH2, this would be CH2, and this would be CH3. Or you could write it as the whole molecule, so you could write CH3, CH2, 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 CH3. I won't bother writing it. You can imagine that part. So we could do that. But we could also use a more organic chemistry way of drawing it, which is what I did first, which is just this wiggly line. We imagine that these bonds here, so on this carbon there are two hydrogens, H and H. We imagine that this is nearly tetrahedral, and so this angle is about 109.5 degrees, and so we've got some kind of more than a right angle in here, which is why we can draw it as approximately this open M. But this is not the only isomer of ethane, propane, butane, pentane that we could possibly have. We can move this methyl group, for example, onto this position to get isopentane. And we could, of course, move another one as well. The possible isomers are obviously relatively varied, but only when we get into longer chains, then we can have more and more complicated things. So that's one type of isomer that we could have, and that's the fairly standard form. If we do it in school or old style, we would call this N-pentane, and then this would be isopentane. And depending on how many isomers we have, we run into a name problem. We mentioned at the beginning that we can then assign these positions and call this then 2-methyl butane, because we want to assign it the lowest number and move it, so we're going to orient it the other way around, call this 1, this one's 2 position, and we can give it the lowest number. But that's not the type that I'm interested in today. What I'm more interested in today is how to give names and how to draw other types of isomers, which are stereoisomers and double bond isomers and ring isomers. So let's imagine one of those. So pen again. That's a red one. We get black. So this would be our first isomer. We've got a double bond, and it's got a group on both sides. We can possibly have these two variants, and we can name them separate names. So why are they separate variants? Well, this double bond has the normal S bond, the normal sigma bond in the middle, and it has a pi bond on the outside. So it's really on the top and the bottom, but we like to draw it as an equal sign. So in reality, looking at the orbitals, we would have the sp orbital in the middle, and then we would have a p orbital vertically, which is combining to form the bond. So let's draw the bonding orbital of that. The bonding orbital of that would be this here. That's our double bond bonding orbital on the top and the bottom. It's got an anti-bonding orbital, which we will have investigated, which we've started to investigate in other subjects. The anti-bonding orbital is outside. That makes logical sense, because if we've got a bonding orbital, it's got to have the electrons between the positive charge of the nucleus to hold them together. So this bond here is obviously the better bond, because it's right in the middle. This bond on the outside, the second bond, is weaker. It's on the outside. And if we want to form an antibond, it would have to be the antibond to this one is out here, and the antibond to the double bond is out here, and it has about the same symmetry as the bond itself. So that all makes sense. What it means is that without breaking this bond, we can't rotate this anymore. So we had our molecule. Let me try and get one. So this is a molecule. We have a molecule, and these bonds can rotate, which means that the position of this blue nitrogen, we can call it, or this green halogen atom, are not fixed compared to this carbon. So we can rotate it to move it. Obviously, there will be positions where they interact more strongly with the hydrogen on here, and there will be positions where they interact less strongly. And there will be obviously preferred positions for this molecule. But there is a lowest, but there is nothing stopping it from rotating. Here on the double bond, which will be this one here, this is a double bond, you can see, because it's triangular. We can't rotate in this direction. The model is not very good at showing that, but the drawing is. We can't rotate in this direction. So these two molecules are different molecules. It is not easy to get from this one to this one. We can get there by breaking the double bond temporarily, rotating the molecule and then forming it again. But we have to break a bond. Alternatively, we could break this bond and form it on the other side, depending on what chemistry we have available to us. So we want to name these possible configurations, the isomers of this one's butene. This would be cis-butene, because we're looking at the configuration between these two groups on the end. Cis meaning on the same side, and trans, the opposite, meaning opposite to. Trans is easier to remember because it's used in all kinds of things to mean crossing over. So you have a Trans Germany Express or Trans-Siberian Railway, which goes across from one to the other. So it's a much more common use. The cis is not used quite so often, but it means on the same side. But what happens if we make the molecule more complicated? So now we've got a chain on this side, we've got a fork chain on this side. They're the same amount of carbons, but this one is longer. And on this one, we've got a bromine and we've got a methyl group. So now we've made life complicated. Well, how do we decide? How do we define which ones are going to be the ones that we're going to control, we're going to decide to name this bond after? Because they do have different configurations. These are not the same molecule. They contain the same groups, so they're identical chemically, except that this bond has a different configuration. It's rotated. So it's the same bond, it's the same molecule in atoms, it's the same order of atoms in if we follow them along, but this bond has a different configuration. It's rotated. That means it will be good to be able to decide which one is which. And to do this, we have a system so that we can assign these groups priority, so that we can give them first and second priority on each end of the bond, so that we can then define whether they're the two lowest priority, the two most significant ones, are on the same side or on an opposite side. And this gives us a new way of naming these two, which is E and Z. The good thing about this is that it carries forward to the next subject, which is optical stereocenters. So we need a set of rules, and those are known as the CIP set of rules that we use to define priority of these things, so to give them a number, an order. So what we're going to do is we're going to take this atom here, and we're going to consider what's connected to it. So first of all, this one and this one are our first atom that we're looking at, one away from our center. And typically we would look at the mass of those atoms first. These are both the same because they're 12s. If we look at the other end, they're not the same. We've got a bromine and we've got a carbon. This is a CH3. Let's put this on. This is a CH2. This is a CH carbon, two carbons. So first of all, this one, the bromine atom weighs more. It has a higher atomic mass than the carbon atom. And so this one is going to be our first number, and this one will be the second one. On the other end, we've got a tie. We've got carbon, and we've got carbon, so they're the same. If one of them was carbon 12 and the other one was carbon 14, the carbon 14 would win, but only if the other parts of the molecule is the same. Because obviously they're both still carbon. If they're not both the same atom, then we can do the same here. So we've got the same number here, we've got 12, and so we need to go further. The next atom here is a carbon, and we've got two hydrogens. So we've got, on this carbon, we've got one carbon and two hydrogens. On this carbon, we've got one hydrogen and two carbons. So this one is going to be set as 1, and this one's going to be 2 on this side, and we can see that this is the equivalent of the cis isomer. It's not going to be called the cis isomer because this notation doesn't use cis and trans. It uses a very slightly different naming convention. It actually uses a German system. So this particular one with them on the same side is the Z isomer. Whoops. And if they're on the opposite side, they would be the E isomer. Sorry about the wiggliness. So if we have this is also the E isomer, because obviously we've got a 12 and we've got a 1 on this side. So this would be 1 and this would be 2. And this would be, oops, I've drawn this wrong. Sorry. This would be 1 and this would be 2. So we've got opposite and we've got the same. There is a confusing bit because the Z obviously looks like their opposite. This looks more like a Z to me than this does. So there's a confusing opposite shape with the letters that they use. This stands for opposite in German, and this stands for together in German. Maybe you know this word, zusammen. The other one is not as common a word for us foreign people to be using. So for memory's sake, it's easier to just remember 1, the Z for zusammen, which means together. There is a new problem, however. What if we have, let's change our isomer up here, so it's unknown. What if we have a double bond on there? So we've got to have something that is similar, and we end up with a double bond on there. What do we do now? If we do it just by mass, this one is going to win because there are less hydrogens on this one. But the convention is in fact the other way round. The convention breaks this bond and imagines that on both ends of it, there's the same thing that would be on the end. So if we take this bond, there's a CH2 on the end of here. So this would be CH2. And there's C and the whole of the rest of the molecule on here. So there's C and all of the rest of the molecule on here. That would be a CH. So if we go along here, we've got this imaginary 2 sets of molecules. It's called divide and copy. It's kind of dumb, but that's how the convention works. So in this case, we go 1 carbon away, that's 12. We go 1 further away, we've got a carbon, and we've got 2 hydrogens. So we've got 12 and 2 is 14, but in this case, we've got 2 12s and the hydrogen. So we've got 25, which would be this being the first priority one. The other rule is if we've got another double bond stereocenter and the molecule is otherwise identical, then the E and Z take priority and the Z is first priority in that case. But that's rarely, if ever, going to happen. There are a whole lot of articles about this on the internet. There's even a Wikipedia on Ian Z and Khan Ingold, whatever the other guy is called. Hang on, I'll look it up. Prelog. So there is a whole Wikipedia article on both, and it's relatively okay to understand. It's just a principle, it's just a priority rule so that we can define things. So it's a convention. There isn't necessarily any logic in it. It doesn't mean that one of them reacts faster than the other. But there is a difference between the two molecules, and for biology, it matters. For other things, it also matters, because if we imagine, if we imagine the two that we had to start with, there is a big difference between these two molecules in that, let's have a longer chain, 1, 2, 1, 2, 1, 2. So these are two identical chains that just have one thing different, and that is whether this bond is E or Z, or cis or trans. This is the cis or Z form. Now we've got the two isomers, and we can look at what possibilities they have. We can see if we stack this, because this angle, this bond angle, is very similar to this bond angle, whereas this one is completely different. It breaks the symmetry. This one will crystallize much better than this one does. It means that the melting point of a trans isomer is higher than the melting point of a cis isomer, which is what we see in our body, in the phospholipids in the cells of our body. Why are trans fatty acids bad? Why is trans fat known to be a bad thing? Because if you have a trans fat, your body selects it, because your body is only selecting for double bonds, so it discovers that there is a double bond in it, so your body will build this into your cell just as much as it builds this cis form in. But the point, the whole reason that that biology tends to choose double bonds is to manipulate the fluidity, effectively, of the cell wall, which allows things to go through. And so there's a certain amount of unsaturated fatty acids in our cell walls and a certain amount of saturated fatty acids, and the unsaturated fatty acids are naturally all cis. They're all this form. They're all Z. And they tend to reduce the melting point. They tend to make it more liquid, and so they allow things to get through. They allow the proteins to move around inside the cell wall. So that's what they're there for. And if they are replaced with trans fatty acids, trans unsaturated fatty acids, these ones, then they behave just the same as if they were saturated. And so that ruins the whole principle for the body. And because our biology is unused to seeing these, it is fooled by them completely. That's unfortunate. If we look at these alternatively, we can see that there are two hydrogens on here, and there's a hydrogen up here, that these two groups might, if they're big enough, they might interfere with each other on this side, whereas these two groups are on opposite sides. They're not going to interfere with each other at all. There's only a hydrogen on the side. And so there might be a higher strain in this molecule than there is in this one. If we try to build them with our molecule kit, we can see that there is really not very much space at all. I'll do that now. So there is my trans or cis or E double bond. We've only got a methyl group on there. That's the smallest thing that we could possibly have. Well, almost the smallest thing. So we've got a trans double bond. You can't see the second bond on here, but these have only got 3 on, so they're obviously a carbon that would be in a double bond. The model doesn't model double bonds very well. We can see this is relatively low energy because they don't interfere with each other at all. There's nothing really close to each other. But look what happens when I rotate it. Obviously, you can't rotate it normally. There isn't a lot of space between these two methyl groups on the end. They're getting very close. It's closer than a bond in this hole here. So these are not going to be able to rotate very easily compared to each other. There will be some kind of energy cost of having this cis or Z type molecule just by the two groups repelling each other and bending everything out of its normal angle. So that costs a bit of energy. So if we allow it to rotate, it will rotate to this position. If it was not a double bond, it will be in some position in between so that none of the bonds are on top of each other. Okay, so we've established that these bonds rotating is a significant part of our organic chemistry. So I'm just looking at a single bond right now. If we look at this particular one, and don't worry that the back atom, let's make it the back atom, is yellow. So these are, we see these as two carbons. This is a chlorine, and the white ones, there are two white ones, there are two hydrogens on each end. Then we can see that this would be probably the lowest energy configuration. So if I rotate it to there, we've got the, so you look at it from the end, you can see that they're off by half. So that would be the eclipsed, where they're over each other. Whoops, it's hard to get it to align with the camera because the camera isn't in the same direction as me. So that would be what we call the eclipsed configuration, where they're over each other. That's obviously going to be more difficult because these things are going to repel each other. And the worst possible one, let's put it to the side, would be where the two big atoms, the two chlorines, are on top of each other because they're bigger than the hydrogens. Obviously, in this case, it doesn't matter. This molecule can rotate into any position there, but if we make these bigger and bigger and bigger, they're going to interfere with each other more and more and make this rotation more and more difficult, higher in energy. In a normal case, molecules like this are rotating the whole time, so there's no chemical difference between rotamers, between rotary isomers, apart from the case that we just had, where there's a double bond stopping them. There is another way to stop a bond rotating, and that would be to make the rest of the molecule into a ring. We can do that in a moment, but first of all, I'm interested in these particular rotamers. So if we look from the end, we can see we can rotate this end bond to any configuration we want. And you would expect to see the energy go up, that will be the highest energy, down, up again when we're eclipsing, but not as high this time because we've got the chlorines on top of hydrogens, down to the lowest possible energy, and then up and down again. Finally back to the first position. There isn't a difference whether we rotate clockwise or anti-clockwise because they're the same. And whether we rotate the molecule in this direction makes no difference. So let's go on to a cyclic molecule. So this is a cyclopentane. Okay, we've got some heteroatoms in there, but we'll ignore those. To start with, the colors of these, they're all tetrahedral atoms. They're all different colors because I don't have that many black ones in my kit. But we can see in this cyclopentane that there is two chlorines on one side and two hydrogens on the other side, and just like a double bond, these are fixed. They can't actually escape. We can't rotate this through and turn the whole ring inside out. In a real molecule, it is also the case. We can't turn the whole ring inside out. And so this molecule, with the chlorines on opposite sides, is different to the molecule with them on the same side. They're not the same thing. They can't switch to form, to go from one to the other. Whereas the rotamers, the rotary isomers, can, unless there's a double bond in there. It turns out that a ring behaves very similarly to a double bond. It means that there are two less hydrogens in the system. So if we count the carbons and hydrogens and compare them to each other, then a ring is, from that point of view, also the same as a double bond. And it is also preventing this isomerization. Okay, so now I want to introduce the chiral center, which is a carbon, a tetrahedral carbon, with four different things on it. So in this case, I've got a blue, a green, a white, and a red-white, an OH group on, now a yellow carbon center, and it has two possible configurations. The two possible configurations are difficult to see, but if we look at, if we fix these green and blue flat, with the green at the top and the blue on the bottom, the yellow one is pointing toward, the white one is pointing towards us, and the red one is in plane. If we switch those over, like this, to put the white one here, we can't rotate this molecule to get it to the position it was before. So if I put the red one down, it flips the green and the blue over. If I put the green and the blue where I want them to be, then the red one is pointing out instead of the white one. So there isn't a way of superimposing the two molecules on top of each other. I'll make another one. Okay, so I've got two molecules now. These are two identical molecules, because if I hold, it's really hard to hold them. If I hold them on top of each other, I've got the green up here, the blue here, the OH on the top, pointing towards you, and this hydrogen to the side. So if I now switch them over on one of them, let's just switch any two. It doesn't actually matter which two we switch over. Then we end up with this, with these two molecules that are not the same molecule. Let me hold them both by the green and put it at the top. So if I have the green at the top, like that, and the blue to the right, then you can see that the OH is either on the bottom or it's pointing towards you. So they're not the same molecule. If we organize them like this, so underneath my hand are two green atoms. Pointing towards you are two hydrogens. Pointing to the right are two blue atoms, which will be nitrogens. And pointing to the left are the OH groups. And I've organized them like this to show you that they are a reflection of each other. So where my hand is would be a plane of reflection. It's sometimes easier to draw this, but all of this is really, initially, at least for today, my plan is that you accept that there are two different types of molecules, that they're reflections of each other, or at least there is a problem there, and that we need to be able to find ways of drawing molecules to show the difference. And then we will have to describe different ways that we can draw molecules, different conventions that we can use so that we can describe this. Obviously, because molecules can get very big and because they're very confusing to look at, it becomes important to be able to simplify them. We introduced the ziggy-zaggy without hydrogens drawing, but that's not going to help us here, because if we need 4 substituents on 1 carbon, it's not going to simplify in that way. Obviously, if one of them's a hydrogen, we don't have to draw that one, but that still doesn't make life very much easier. So we need some other ways of drawing it, and there are a whole lot of conventions that we can use, some of which work better for some molecules, others work better for other molecules, and so it turns out that some are used more often for biomolecules in biology, some are used more often in organic chemistry, some are used more often in other subjects. But we need all of them typically because we might see them. The whole point of organic chemistry for you is that you can converse with people who are actually doing organic chemistry, and so if they show you a drawing, it will be good to be able to at least understand what it's showing.